So we're going to begin the third lecture by looking at multi-electron atoms. So we've seen how the spin or the orbital angular momentum of electron gives rise to a magnetic moment. We've done this for the hydrogen atom and just a single electron. Now, of course, that's not particularly applicable to materials. We want to be able to look at multi-electron atoms and find their total angular momentum. Okay. So the idea is that something like copper would have a number of electrons. Those electrons will have potentially orbital angular momentum and spin angular momentum. What we'd like to be able to do is sort of zoom out a little bit and say, rather than thinking about all of the electrons individually, we'd like to be able to say, what is the total angular momentum and what is the total magnetic moment of that atom or that ion? Okay. So that would involve finding a total orbital angular momentum, a total spin angular momentum, and adding them together to get the net angular momentum. Okay. But we're able to use, now we could do, as you've seen, you can solve the Schrödinger equation exactly for a one electron atom, so hydrogen. But you can't solve the Schrödinger equation with a pen and paper for even two electrons. So helium is already too complicated. You could do a calculation, you could get a computer, and you could do a calculation and try and solve Schrödinger's equation for a multi-electron atom. It's actually quite challenging and quite intensive. And that would tell us the total magnetic moment if we did an accurate enough calculation. But actually, what we find is that we can get a reasonably good idea of what's happening in these ions, good enough to understand the paramagnetic behavior, by starting with the simple one electron picture from the hydrogen atom with the 3 quantum numbers or the 4 quantum numbers that we've learnt about in the hydrogen atom, and seeing how we can use that to build up a picture of the multi-electron atom. So the first thing to do is to use the Pauli exclusion principle, which tells us that every electronic state needs to have a unique set of quantum numbers. Okay, and that will enable us to find the electronic configuration. So I've given here the example 1s2, 2s2, 2p6, 3s1. Okay, that's the electronic configuration where we've specified the n and the l quantum numbers. We can then use Hund's rules, which will give us the angular momentum configuration. So that's the ml and the ms for each electron. And when we have that, we can use some other empirical rules to work out the total angular momentum. So first of all, let me introduce two further quantities. Okay, I'm going to define capital L as the sum of all the ml for each of the electrons. So each electron's got its own set of quantum numbers, its own value of ml. And if we sum those together over the electrons, we will get capital L. And if we sum the spins of all the electrons, we will get a quantity I'm going to call capital S. Okay. Now we can then combine capital L and capital S to get the total angular momentum for the atom, which I give the letter capital J. Okay. So there are many different ways of adding up angular momentum, and Hund's rules allows us to predict the most stable, the lowest energy configuration. So I won't go into the basis of where Hund's rules come from. I will just simply state them here, which is that we want the configuration that maximizes big S, that maximizes big L, and then if the shell is less than half full, we take this first definition, J is mod L minus S, and otherwise J is equal to L plus S. Now, if the shell is exactly half full, those two definitions are the same. They give the same value of J, so there's no problem there. The first thing to note perhaps is that if I have a closed shell, big L and big S will be 0. Let's just see what I mean by that. So I like to draw these little box diagrams. So let's draw one of these, and I want 5 divisions. 1, 2, 3, 4, 5. Okay. And what I'll put on the top is ML. So let's see, this should be -2. I've done a D state, -1, 0. No, +2 first. Yes, +2 first makes more sense. -1, -2. Okay. And if I completely fill this, so that's a spin up and spin down, spin up and spin down, spin up and spin down. So there we have 5 electrons. Okay. So 5 of the electrons are spin up, and the other half are spin down. Okay. Then you can see that in this case, L is equal to 0 and S is equal to 0. L is equal to 0 because +2, +2, -2, +1, -1, 0 added together gives me 0, and S is 0 because plus and minus are half for each of these pairs. Okay, so when we're trying to work out the angular momentum, we don't have to deal with any filled shells or any even completed angular momentum. So if the P is full, if the S is full, I'm only dealing with the one that's the valence one, the one that's partially empty. Okay. Now, I think the best way to get a handle on what Hund's rules are doing is simply to do some examples. Okay. So let's have a go at a couple of examples. You can, of course, just pause the video and after I've written each of these down, and you can have a go yourself if you're feeling confident. Okay, so let's have a look at some of these. So I'm going to do 4. So let's do cerium 3+. Okay, now that has the configuration of a noble gas, xenon, and its outer configuration is 4F1. So I need to come up with one of my little box diagrams. These are not essential, just the way I like to draw it. Let's see, so it's F, so I'm going to need 7 of these. 1, 2, 3, 4, 5, 6. I'll put the value of ML at the top just for reference. 3, 2, 1, 0, -1, -2, -3. Okay, and the only thing I can do here, my 1 electron, so what do I want to do? I want to maximize S. That tells me the electron is pointing up. So I need to put 1 in and it's going to be pointing up. And I need to maximize L. Well, I should put it in the state with the greatest value of ML. So it will go there. Okay, so in this case, L, well, I've only got 1 to sum, so that gives me 3. S, well, that's going to be just a half. And J, because this is less than half full, is going to be the difference of these two. So this will be 5 halves. Okay. So now for the cerium atom, which contains lots and lots and lots of electrons, I can zoom out and just replace that by saying this is an object which has orbital angular momentum 3, spin angular momentum 1/2, and the total angular momentum of 5 halves, or at least those are the quantum numbers which go to describe the angular momentum. Okay. Right, so let's see if we have, picking the unusual elements today, holmium 3+. So that is a xenon core, and it's 4F10. All right, so same as before, draw my box diagram. 1, 2, 3, 4, 5, 6. 3, 2, 1, 0, -1, -2, -3. Okay, 10 electrons. I want to maximize S. Well, that's going to mean that 7 of them should point up and 3 of them should point down. Okay. To maximize, well, 7 of them are pointing up. I got no choice with those. Let's just pop them. Let's just pop them in. 5, 6, 7. So I now need to find where to put the last 3. So at the moment, this half-filled shell has L as big L is 0. So my last 3, well, I want to put them in the states that have the maximum ml. So I'll put one there, and one there. So that would give me L is equal to 3 plus 2 plus 1, which is 6. The 3 paired electrons don't give me any contribution to S, but I have 4 unpaired ones. So that would give me S is 2, summing up 4 halves. And it's more than half full, so I need to add these together. So J is equal to 8. Okay, relatively large angular momentum state. Okay, let's look at 2 D elements. Okay, so we'll do vanadium 3+. Okay, that is an argon core, and its valence configuration is 3D2. So now this is D, so there are 5 values of ml. D is, remember, L is 2. So 1, 2, 3, 4, and ml is 2, 1, 0, minus 1, minus 2. Okay, right, D2, I've got 2 to put in. Maximize S, they're both pointing up. Maximize L, well, they should go into the maximum ml states. So L is equal to 3. S is equal to a half plus a half, which is just 1. Less than half full, so we need the difference of them. J is equal to 2. All right, manganese 3+. This is an argon core and 3D4. Okay, same box diagram. 1, 2, 3, 4. Maximize S, so 4 of them are pointing up. Maximize L, well, they're going to have to be 1, 2, 3, and the 4th. Okay, so this is telling me that L is equal to 2, S is equal to 2, and J must be equal to 0. Okay, so that's interesting. I've got something in which the spin angular momentum and the orbital angular momentum seemingly cancel each other out, giving no net angular momentum. Okay, so the next short video, we will then need to think about if we've got the total angular momentum of our atom or ion, what does that mean for its magnetic moment?